Hi, this is part two to the lecture of chapter 9. In this lecture, we're going to go over large sample test about the difference in two population means. Okay. Large sample test about the difference in two population means, and the large sample test about the difference in population proportions. The large sample test about the population mean and the large sample test about the population proportion and the introduction of what hypothesis testing is found in part one of, of the lecture for chapter 9. Okay, so let's scroll and look for the section that involves the large sample test for the difference in two population means. Okay. All right. Uh, oh, keep scrolling, keep scrolling. Oh, there it is. Okay, this is section 4, large sample test of hypothesis for the difference between two population means. Okay, and this type of test involves us collecting data on two two different populations. So we get a sample from population 1 and population 2. What are two distinct populations? Say salmon and tuna. Turkeys in New York, turkeys in Pennsylvania, men, women, Ford cars, Hyundai cars, electric cars, gasoline cars. And what we want to do is see if the average uh, of some characteristic is different between the two populations. Say the number of eggs salmon lay uh, and the number of eggs tuna lay, are they different? Okay, or are they the same? On average, if salmons lay about the same number of eggs as tunas, then the difference between the two population means of salmon eggs and tuna eggs should be 0. Okay, so let's write this out. Oh. Okay. So we have the average uh, eggs for tuna, and then we have the average number of eggs that salmon's lay. And if the average number of eggs that salmon lays minus the average number of eggs that tunas lay are no different, then we should expect the difference in the average to be 0. Or maybe salmons lay more eggs than tunas, then we should expect this difference to be greater than 0. But if salmons lay less eggs than tuna, then we should expect this difference in the averages to be less than 0. Okay, so that's the kind of testing we are going to do here. Okay, assumptions. Again, to apply the normal distribution and the standard normal distribution, we need to make sure the sample that we collect from each of the different populations has to be greater than equal to 30. The sample collected from population 1 and the sample collected from population 2, both of them have to be greater than or equal to 30. Okay? Again, the samples have to be randomly and independently selected. That's a given as well. So the population parameters are mu1 for population 1 minus mu2 is population 2. And the sample mean differences is x1 bar minus x2 bar. Okay, this is representative. These sample mean differences are representative of the population mean differences. Okay, and we want to test if this population difference is greater than, equal to, or less than some D naught. In this example that I gave previously about salmon eggs, the D naught, the hypothesized difference, was 0. Okay, but it doesn't have to be. It could be 3, it could be 5, or whatever. And if we said, say, if population average of salmon eggs minus the population average of tuna eggs is equal to 3, that means salmons lay 3 more eggs on average than tunas. Okay, that's what that means. Okay, let's keep going. Again, when we're doing hypothesis testing, we need to calculate the t-statistic. I mean, not the t-statistic. I'm sorry, that's in chapter 10. The z-score, the z-statistic. And this involves calculation of the standard error. And the standard error, or the standard deviation of the differences in the sample averages, is equal to the following. In an ideal world, it'd be the population 1 standard variance divided by n, the sample size from population 1 plus the variance of population 2 divided by the sample size of population from the sample from population 2. And that whole thing is square rooted. However, the standard deviation of population 1 and the standard deviation of population 2, actually, we square it, right? So these are the variances, are not known 99.9999% of the time. Therefore, we use the variance from the sample of population 1 and the variance of the sample from population 2, okay? And that's approximately equal to the true value. All right? Okay, so how do we do our testing? Well, this is the mechanical testing procedure, right? It's exactly the same as before. We have to create a hypothesis. The hypothesis either has 2 one-tail tests, either is a one-tail test, a left tail or a right tail, or a two-tail test. If it's a left tail, one-tail test, it'd be the H naught, the null hypothesis, is mu1 minus mu2 is greater than or equal to D naught. And the alternative is the opposite day, or mu1 minus mu2 is strictly less than D naught. If it's a right tail test, the null hypothesis is mu1 minus mu2 is less than or equal to D naught. And the null hypothesis, the alternative hypothesis is mu1 minus mu2 is strictly greater than D naught. If it's a two-tail test, the null hypothesis is the difference is equal to D naught, and the alternative is not equal. Okay, so we would accept the alternative if the difference is greater than D naught, extremely high value, higher than D naught, or extremely low value, below D naught. And D naught is something that we specify, right? That's the test that we're specifying. Usually for many of the tests, D naught is equal to 0. Okay, but it doesn't have to be. The test statistic, here's the test statistic. It's basically the hypothesis, the null hypothesis, divided by the standard error. It's always that. It's a Z statistic because we're assuming normal distribution because N1 and N2 are greater than or equal to 30. So it's a sample mean from population 1 minus sample mean from population 2 minus D naught divided by the standard error. And the standard error, as discussed above, is the variance from population 1 divided by N1 plus variance of population 2 divided by N2. And you square root that whole thingamabob, okay? Obviously, these variances from the population are unknown as discussed above, so we use the variances from the samples. And then the rejection, the testing. We will reject H naught in a one-tail test. If we do a p-value approach, the p-value is less than alpha. The critical value approach, the z, which is going to be a negative number, has to be less than the negative z of alpha. And if it's an upper tail test or a right tail test, we reject H naught if the z is greater than z of alpha. And of course, if it's a two-tail test, we're going to compare the test statistic z with z of half an alpha, okay? And the p-value approach, to calculate the p-value, you have to double the tail area. All of this regarding the rejection is exactly the same for all of the tests, okay? All right, before we move on to the example, let's introduce you to the difference in the population proportions, okay? It's no different. We'll just do it real quickly because it's, again, not much different. Okay, here. Okay, here it is. The large sample test of hypothesis for the difference between two binomial proportions. Again, here, just like the two the means from two different populations, these are proportions or fractions from two different populations. Okay, so we're going to be focused on P1, which is the proportion from population 1, and P2, which is a proportion from population 2. Okay, so one example of this would be something like P1 is equal to proportion of Republicans in LA, while P2 is the proportion of Republicans in San Diego, okay? So LA being one population and San Diego being another population. Now what we care about is P1 minus P2, or how does population proportion of Republicans, or the fraction of Republicans LA, compare to that of those in San Diego. And again, this could be, let's say, we could test whether that is equal to 0. That means there's no difference. There's same fraction number of Republicans in LA relative to the rest of the population in LA, say, like 45% and 45% in San Diego, okay, compared to the population in San Diego. That means there's no difference in the proportion of Republicans in LA compared to its population, and the proportion of Republicans in San Diego compared to its population. If P1 minus P2 is greater than 0, that means the LA has more fraction of its population being Republicans compared to San Diego. And obviously, if it's less than 0, it's the other way around. San Diego has more Republicans as a fraction of its population compared to Los Angeles. Okay, so that's the kind of test we're going to do. All right, let's clear this and move on. Okay, assumptions. Since we have two populations, we need to make sure the sample from both populations are large enough to apply normal distribution. And in order for us to do that, what we are going to use here is P1 hat, that is the samples proportion, and P2 hat is the sample proportion from population 2. P1 hat, which is the sample proportion from population 1 times the sample size of population 1, that has to be greater than 5, and Q1, which is 1 minus P1, times N1 has to be greater than 5, and the same thing has to be true for the sample from population 2. Okay, so we need to have all of these to be greater than or greater than equal to 5. depending on the book, and I'm not going to mark you wrong if you do greater than or equal to, because it depends on the book, frankly. All of these have to be true to assume and apply the normal distribution. Okay. Again, we're testing the difference here, and the standard error of the sample difference is the square root of P1 times Q1 divided by N1 plus P2 times Q2 divided by N2. And all of that, you add them together, and all of that square root, that is the standard error, okay? Now, when we do the hypothesis testing, generally what we are going to do in a more simplified situation in an introductory class like this is we're going to test if this difference is just equal to 0 or not, okay? So we could do a one-tailed test or two-tailed test, but generally we're going to test whether the difference is 0 or not, okay? So that's what we're gonna assume the hypothesized value, the difference is equal to 0. Now, in this type of situation, then that would mean if the difference is indeed 0, then P1 is equal to P2 and equal to P. And Q1, which is 1 minus P1, is equal to Q2 is equal to Q. Remember, if there's no difference between P1 and P2, then that means P1 equals P2, okay? So if we have a two-tailed test, that means P1 minus P2 is equal to 0. That's the null hypothesis. And the alternative is P1 minus P2 is not equal to 0. Nevertheless, we could also do a one-tailed test. And in this situation, the null could be P1 minus P2 is greater than or equal to 0. And the alternative is strictly less than 0. And the right tail is the opposite case, where the null is P1 minus P2 is less than or equal to 0, and the alternative is P1 minus P2 strictly greater than 0. The test statistic is the sample estimate of P1 minus the sample estimate of P2 minus 0. Remember, this is usually what we're going to do, is we're going to, in an introductory class, is just stick with 0. Divided by the standard error, which is right here. So substitute that in for standard error, and this is what the test statistic looks like, okay? Now, we can simplify the standard error slightly. Again, given the null hypothesis is true, and that's how we always do our testing, then P1 is equal to P2, right? And Q1 is equal to Q2. That's from here, okay? If we assume that the difference is equal to 0, then P1 is equal to P2, and then Q1 is equal to Q2. And we said, well, P1 is equal to P2 is equal to P, and Q1 is equal to Q2 is equal to Q. And we're going to substitute that in, okay, here into the bottom right here. And we get P times Q divided by N1 plus P times Q divided by N2. And you add them together and square root it, okay? So this is supposedly simplifies it. I don't know. When I do it, it's about the same level of difficulty or whatever, okay? And we don't know what P and Q are. If we did, we wouldn't have to do any of these testing. And because we don't know, what we're going to use is the pooled sample P hat, where P hat is x1 plus x2 divided by n1 plus n2. So you get the sample of correct, quote unquote, the correct ones from population 1 plus the sample that is quote unquote correct. In my example, it would have been the Republicans, right? sample of Republicans from LA plus sample of Republicans from San Diego. You add them together, divide it by the sample that you collected from LA plus the sample that you collected from San Diego. Okay. And that would be the pooled p hat. Okay. And you could even simplify this slightly and you can make it like this. Okay. By plugging in the sampled p hats, p hat times 1 minus p hat, which is just q hat, times 1 over n1 plus 1 over n2, parentheses, okay? You plug this in for the standard error, okay? And we get this right here, okay? Now, this is what the z statistic becomes, or the test statistic, okay? And then rejection is identical as before, the testing part. You have the critical value approach and the p-value approach. In a one-tail test, left tail is z, which is a negative number, is less than negative z of alpha. Right tail is z is greater than z of alpha. The two-tail test is you compare the test statistic z with z of half an alpha. And the p-value is the p-value has to be less than alpha. All of this, if these are true, one of these are true, then you reject the H naught, right? These are the criteria to reject H naught. And if it's a two-tailed test, the p-value, you get the tail probability and you double it, okay? All right. Given that I did a quick overview, or I did an overview of how to do a large sample test of the difference in the population means and the difference in the population proportions, let's do some examples. Okay, let's scroll up and do a couple examples for the difference in population means first, and then we'll do the one for population proportions after. So here it is. Okay, here's section 4. Scroll down. And we'll do example 9. Okay. Yeah, let's do example 9. Okay. We could do example 10 too if you want. Okay. Example 9.9. To determine whether car ownership affects a student's academic achievement, a random sample of 100 car owners and 100 non-car owners were drawn from the student body. Okay, so we got a sample. I'm going to make a little table and put car owners and non-car owners. Okay. And we got a sample of 100 from them and 100 from these guys. Okay. Okay. When the sample is drawn, the grade point average from the non-car owners, okay, had an average of 2.70 and a variance of 0.38. So we have X bar, which is the GPA, X bar, and we have S to the squared. Oh, let's do small s. Okay, which is the variance. And for for non-car owners, it's 2.70. And the variance is 0.36. And for the car, while for the car owners is 2.54, this is not written well. While for the car owners, it's 2.54 and 0.40. Okay. Now, one thing to note here is that I'm going to use the non-car owners as population 1 and the car owners as population 2. And the reason I do that is when I take the difference, you usually want to use the bigger number, the bigger sample average, as the population 1. So the difference is positive. And this is just easier to discuss and present. It's just kind of a rule of thumb issue. Um, and that's all. You can do the testing the other way, and that's totally fine. But I find that using the bigger average, sample average, the bigger number here as for population 1 to be easier to do, easier for me to do the analysis, okay? And to present. It's just a rule of thumb thing, okay? So that's why I switched it for pot one. I'm going to do this as population, okay? And population 1 is the non-car owners because their GPA is higher than for car owners for the sample, which is 2.54. All right. And they say, do this test. Do the data present sufficient evidence to indicate a difference in the mean achievements between car owners and non-car owners? Fancy a way of saying, do having a car reduce change the GPA? Okay, that's basically what they're trying to say. Okay, change the GPA. Is there a difference? So likely this is it's a two-tailed test. And they say test using an alpha of 5%. So alpha is 5%. Okay. All right. So we got everything we need out. And the first thing we need to do is set up the hypothesis. Hypothesis. And we need to set up the null and the alternative. And the null is mu1 minus mu2 is equal to 0. Remember, the equality part has to be part of the null. And then the copy and paste. Okay. And then for the alternative hypothesis, it's going to be that the difference in the population mean GPA for non-car owners and the car owners is not equal to 0. So there is a difference. That's the alternative. Okay. And for simplicity and for completeness, I'm going to put D naught, the hypothesized difference, that is equal to 0. I'm going to put that out there as a separate line to do the analysis. Okay. See that D naught is equal to 0. Use a big D. Oh, all right. The next thing we got to do is create the test statistic. Okay. And when we create the test statistic, we need to calculate the standard error. And if we go up here, this is the test statistic. So we need the standard error. And the standard error is right here. Huh? It's the variance from population 1 divided by the sample from population 1 plus the variance of population 2 divided by the sample of population 2. Okay. And we're going to use the sample variances because we don't know the population variances. Now to do this seems, and we got to add these two fractions together and then take the square root. And that can be difficult to do for a novice in Excel. So we're going to do it in parts. The first part, I'm going to do it in 3 parts. Part 1, part 2, and part 3. Part 1 is going to calculate population 1 ratio. Part 2 is population 2 ratio. So let's do it this way. Okay, let me write this out. So this is going to be part 1. That's going to be calculating this. Part 2 is calculating that. Part 3 is just summing the two. Part 1 plus part 2. And then for lastly, for the standard error, I'm just taking the square root of part 3. Okay. So I'm going to break it up into those parts. Let me clear this because it's kind of messy. You can see the formula. All right, so let's do this. Part 1. Part 1 is just sample variance divided by sample size. Part 2 is sample variance for population 2 divided by sample size from population 2. Okay, here they are. And let's just standardize the number of decimal places. Part 3 is you add them together. Okay. And then the standard error is you get part 3 to the 0.5, or you square root it. Ooh, that's a big number, I guess. And there it is. Let's see if we did this correctly in the solutions part. Oh, well, I didn't even calculate it. Okay, well, let's we'll figure it out when we calculate the z-score or the test statistic. And that is equal to, okay, that is equal to sample average from population 1 minus the sample average from population 2 minus, okay, you could even put the hypotheses, but that doesn't matter, minus D naught, okay, and this whole thing has to be bracketed, divided by the standard error. And it looks like we calculated everything correctly because that equals to the number in the notes. Okay. So we have our test statistic. We calculated that. We have our hypothesis. Next step is to do the testing. And the testing we could do in 2 different ways. We could do the critical value approach. And we're also going to use apply the, let me delete this row so we could have some space. We could also do the p-value approach. To do the critical value approach, we're going to compare the test statistic with the critical value that creates a right tail of alpha. Okay, so the test, so that's, we have the test statistic, it's 1.8353, and now we got to find the critical value. And to do the, oh, I forgot, the critical value, we have an alpha, and that is equal to this. Okay. 5%. And I just realized this is a two-tailed test. So in a two-tailed test, I need half an alpha. So alpha divided by 2, which is a half an alpha. Okay. And then because Excel calculates a cumulative from left to right, right? So we need 1 minus half an alpha. This is equal to 1 minus that guy. And then here we could do the critical value. Calculate that. This is norm.s.inv. The cutoff that creates 97.5% to the left and 2.5% to the right. Okay. Is that number. Okay. So then we have critical value, question mark, test statistic. And this is the critical value. And the test statistic is this. And we could see the critical value is greater than the test statistic. So that means we are going to fail to reject. Fail to reject. And right here, we fail to reject specifically H naught, which is right here. Okay, H naught cannot be rejected. Fail to reject H naught because the test statistic is closer to the middle or zero, closer to zero than the critical value. Okay, to reject, we need the test statistic to be further away from zero than the critical value. All right, now let's do the p-value approach. Okay. And this is again a two-tailed test. So for the p-value approach, we have a test statistic of 1.8353. Okay. And so what we need to do is we know the cumulative, and this is going to be equal to norm.s.inv, sorry, .dist, and we put this cutoff, and remember Excel calculates from left to right, but we need the right tail, and we do cumulative of true. We get this probability right here. So then the right tail, this is equal to 1 minus cumulative, it's 3.32. But we have to double this to calculate the p-value. P-value is this times 2, okay? This is a two-tailed test. And then we do a comparison of p-value, question mark, and alpha. And the p-value is 6%. Alpha is 5%. So the p-value is greater than alpha. And again, we fail to reject because we could only reject if the p-value is equal to alpha. Okay, again, that's up here in a two-tailed test. P-value is less than alpha. We could reject the null hypothesis, rejection region. Reject a null when this is true right here. Okay. Okay. So what does this mean? We fail to reject the null that the average GPA for car owners and the average GPA for non-car owners, car owners and non-car owners are equal. We fail to reject that. So we reject the alternative that car owners and non-car owners have different GPA, meaning it's likely that the car may not have an impact on the GPA. There's insufficient evidence to declare a difference in the average academic achievement for the two groups. Okay. We're not accepting this, we're failing to reject this. Okay. And we have to basically say we don't have any evidence to say the alternative is true. All right, let's do another one. Okay. We'll do this next one called training center. Training center example. Okay. A standardized exam was given to the individuals who are trained at two different centers to evaluate the differences in education quality between them. Okay, so there's two training. So we'll let, this is population. We'll do 1 and 2. And this is center A and center B. Okay. Mu1 is the mean exam score from population center A. And so we'll say that's population 1. And mu2, population 2, is the mean score from population center B. Okay, and then they took they got some samples, and here's the information from the samples. Okay, some sample summary statistics. And you got sample size is 30 from A and 40 from B. And the sample mean, X bar, or S bar, X bar. And that is 82% and probably 78%. And standard deviation S, this 10 and 10. Okay. And they say this is based on some previous studies, the standard deviation. So likely they're saying this is sigma, but it doesn't matter if it's sigma or S, we're still going to use the tens. Okay. Can you conclude using alpha of 5% that there's no difference exists between the trainings? So again, no difference exists. That means the hypothesis testing. It's two-tailed test. Hypothesis. Okay. So you have the H naught and HA. The null hypothesis is mu1 minus mu2 is equal to 0. And just like before, mu1 minus mu2 is not equal to 0. And so then D naught is equal to 0. Okay, so that's our hypothesis. And the test statistic. Okay. Okay. The test statistic here, we need to calculate the standard error. And again, to calculate the standard error, let's go look at the formula again. Okay. Here it is. It's again complicated, so I'm going to do it in parts. I'll do it in 3 parts again, but you guys could do it in 2 parts or 1 part, or just do it all in one cell, whatever's easiest for you. Part 1 is variance from, but this is sigma, which is the standard deviation. So I need to square it and divide it by n1. So I'm going to put parentheses around this to make sure it's nice and neat and the formula is correct. Okay. Part 2 is sigma to the square divided by, and that whole thing has to be divided by n2. And part 3 is this guy plus this guy. And standard error is this guy to the 0.5. Okay, so that's what it should be. And let's see. And then the test statistic, Z, is equal to X bar from population 1 minus sample average from population 2 minus D naught. And the whole thing has to be divided by the standard error. So, let's go check this. Training center. Yep, test it. 1.66. Okay, perfect. And the standard error is 2.4152, 2.415. Yes, perfect. Is it 2? Yep. Okay. So we did this correctly. And now we got to do the testing. And we could do the critical value approach. I'll do that one always first. And then the p-value approach. I'll do that around here. So to do the critical value approach, we have to, again, we have the test statistic here. and we got to calculate the critical value. And the critical value is the cutoff that creates half an alpha to the right tail. Okay, I almost said alpha again. So let's do that. Alpha is equal to 5%. We know it's a two-tail test. So alpha divided by 2. Okay, that's the right tail. Okay. And then to create the cutoff, I have to do 1 minus alpha divided by 2. Okay, I need that. I need the left tail to do the calculate the critical value, because that's just the way Excel works. So this is equal to norm.s.inv, the cutoff that creates 97.5% on the left and 2.5% on the right. And there it is. Okay. And then we compare the critical value and the statistic, and the critical value is this. The test statistic is that. And the critical value is greater. And again, we're going to fail to reject H naught here, because the critical value is a bigger number, meaning further away from the center or 0 than the test statistic. And you will see that here. Cannot reject is 1.66 compared to 1.96. And let's do the p-value approach, which is right here. We'll do it together. P-value approach. And to calculate the p-value, we need to get the tail, the right tail, but we need to do the cumulative. Yeah, I don't think that's how you spell it. And this is equal to norm dot s dot dist. You know, this is the left tail when the cutoff is the test statistic, and then comma true for the cumulative. But the right tail, I guess I should call that right tail instead of cumulative. This is equal to 1 minus this number. Okay. Yeah, I should call this the left tail. Okay. And then the p-value, this is just double the right tail. And there it is. It's like 10%. Okay, 9.77. So to do the testing, it's p-value, question mark, and alpha. P-value is this dude. Alpha is this dude right there. And you see the p-value is greater than alpha. And that means, again, you fail to reject the null hypothesis. We cannot reject the null hypothesis that the difference in the means are equal to 0. Okay, there's not enough information available to reject the null hypothesis. Okay. Okay. So a proper way of saying the conclusion is right here. At the 5% level of significance, the sample evidence indicates there is no difference in the quality between the, we cannot reject that there is no difference in the quality between training centers, okay? Because we cannot reject the null hypothesis. Okay, so we did 2 examples with the difference in 2 population means. And now let's do 2 examples, or at least however many we could find, for the difference in the population proportions right here. Let's do example this one. Records of a hospital show that 52 men out of 1,000 versus 23 men out of 1,000 are admitted for heart disease. Okay. Do the data present sufficient evidence to indicate a higher rate of heart disease among men? So this looks like it's a one-tailed test than women using alpha of 5%. So let's create the table. So here's population 1 and population 2. And it looks like they both have 1,000 and men 52. So yeah, it looks like men is higher. So we're going to put men as population 1 and women as population 2. Okay. And we got the sample size are both 1,000. And the X is the numbers who have heart disease, 52 men and 23 women. Okay. And we could calculate the P hat for men and women. This is 52 divided by 1,000. And for women, is 23 divided by 1,000. And we could calculate Q hat, just in case we need that. That is equal to 1 minus P hat. Okay. And 1 minus P hat is Q hat. So 94.8% of men do not have heart disease out of 1,000. And 97.7% of women out of 1,000 do not have heart disease. And they say do this with an alpha of 5.00%. Okay, let's do the testing. And so the question they ask is, does the data present enough evidence to indicate that men have higher heart disease rate than women? Okay, higher. So hypothesis, one side is strictly higher. One of the hypotheses, either null or alternative, is strictly higher, and the other one is less than equal to. So likely it's P1 minus P1 minus P2 is greater than 0. Okay, strictly higher. While the null is P1 minus P2 is less than equal to 0. Okay. And again, we in intro class, we're only going to use the difference of equal to 0. All right. Remember, the equality part has to be in the null. Okay. So that's why I knew one side that's strictly higher, that has to be the alternative. Okay. So this is the hypothesis. And given this, we need to calculate the test statistic. Okay. Test statistic. And in order for us to calculate the test statistic, we need to calculate the standard error. And my guess is the test standard error is very difficult. Yet, this is the standard error right here. Okay. And that involves calculating the pooled proportion. So pooled. Okay. Let's do that. So the pooled is just you sum across samples 2,000. The x's is 75 and P hat is that. Probably the average of these two. Yeah. And equal to 1 minus this. That's Q hat. Okay. So that's the pooled P hat and Q hat. All right. So to calculate the standard error, here's the formula. P times Q times 1 over N1 plus 1 over N2. I'm going to do it in 3 parts, just like before. What I'm going to do is I'm going to have this as part 1, this as part 2, and then multiplying it together as part 3, and then square rooting it that as the standard error. All right, so let's do it that way. Maybe that's easier that way. I have no idea. So let's try that. So part 1, part 2, and part 3. So I think I said part 1, I'm going to do p hat times 1 minus p hat or q hat. Okay, cool. I don't times that. I don't want to. I don't want to just look at it as well. We'll use percentages for now. Okay. Part 2 is 1 over n1 plus 1 over n2. 1 divided by 1,000. Oh, those are equal. Okay. Oh, sorry. So this is equal to 1 divided by 1,000 plus 1 divided by 1,000. Okay. I guess I'll use that as a percentage as well. Okay. And part 3 is this times this dude. Okay. And then standard error is part 3 to the 0.5 or square root of that. And there it is. I'll just use it as a percentage. Something like that. Okay. So the test statistic is the difference in the p hats divided by the standard error. So the z is equal to the equal sign. 5.2% minus 2.3% divided by the standard error right here. Now, if you want to do completeness, then you want to set up a template minus hypothesize z d naught, right? But we said here we're usually be equal to 0, but maybe not for future. You want to create a template. Ooh. Did I screw something up? Oh no, because it's a z, and this is not a percentage. So let's go to format cell number, and we'll do like 2 decimal places. Use a comma as well. Change it to a number. Okay. Okay. So z is 3.1, 3.41. So that's our test statistic. Now we're going to do our testing. And for our testing, we could do our critical value approach. Okay. And for and here it is right here. Testing. And this is a one-tailed test, right? So for the critical value approach for a one-tailed test, we have the alpha. We got to create the critical value. We have an alpha of 5%. And then we're going to have to do 1 minus alpha. We don't have to do alpha divided by 2 because it's not a two-tailed test. That's 95%. And the critical value, okay. Oops, sorry. The critical value is the cutoff norm.s.inv is the cutoff that puts 95% to the left and 5% to the right. And critical value, question mark, test statistic. Critical value is 1.64. Test statistic is 3.41. Test statistic is greater. That means we get to reject the null. Check the null hypothesis that men and women have the same rate of heart disease, okay? Or even men has less than or equal to women's rate of heart disease. Likely men have higher rate of heart disease than women, okay? Well, let's do this test again with the p-value approach. Okay? Let's practice doing it both ways, even though in real life you'll only do it one way. Okay, here we have to compare, we have to calculate or construct the p-value using the test statistic and compare it with the alpha of 5%. This is the test statistic, and then the left tail or the cumulative, right? This is equal to norm dot s dot dist, and you put the test statistic in, comma, true, okay? That's the left tail. And then the right tail is the p-value in this case. That is equal to 1 minus that, which is 3%. Okay. And to do the testing, it's the p-value, question mark, alpha. P-value is 0.032%, not even 3%, sorry. And the alpha is 5%. And we could see the p-value is strictly less than the alpha, which means, again, we get to reject the null that men have less than or equal to the heart failure disease rate as women. So if we scroll down, let's look at the answer. It's right here. This is the example right here. Okay, standard error is, yeah, yep. Test statistic 3.41, 3.41. P-value approach, p-value is 0.032% and 5%. Yeah, sorry, I didn't make these percentages. So we get to reject the null. Critical value approach, we compared 3.41, the test statistic, with the critical value of 1.645. Okay. I think it's 645. Yeah. Oh yeah, 49. Okay. All right. And again, we reject the null. Okay. I was going to do this one, but I don't think I provided enough information. So we can't do this one. Yeah, I didn't give you all this information to calculate this. Sorry about that. I don't know why I put an example here and I didn't give you the information to calculate this. Maybe it's above test preparation. Okay. Well, I don't want to deal with having a Zoom recording of me trying to look for this. So we'll do our one example and call it a day. And then the last discussion I'm going to have two. One is that testing, okay? There's a discussion here about testing using confidence interval. Okay. I think it's this. Yep. Confidence interval and using it to perform hypothesis tests. You could do hypothesis tests using, you could also kind of do a hypothesis test using the confidence intervals that we developed in chapter 8. Okay. And this is a note that the alpha, the comfort level or level of significance in the confidence interval analysis is equivalent, is basically equal to the significance level alpha in hypothesis testing. So another way to perform hypothesis testing is to construct a confidence interval with the significant level alpha. If the confidence interval contains the specified H naught value, okay, in this case, the D naught of 0, then the H0 should not be rejected. If the confidence interval does not contain the specified H0 value, then the H0 is rejected at the significance level of alpha. Okay, so here's a quick one right here. Let's construct a 95% confidence interval for the difference in the average academic achievement between car owners and non-car owners. Okay, using the confidence interval, can you conclude that there is a difference in the population mean for the two groups? So we actually did this analysis. Which one is that? Training center. Oh, here it is. Car owners and non-car owners. Okay. All right, so maybe we use this data. Let me see. Okay, to create the confidence interval here, let's create that. The confidence interval, so this would be example 9.10. Okay, so let's create the confidence interval. And because we're going to use the data above here, just going to do it in the same Excel sheet. Okay, it says construct 95% confidence interval. So our confidence interval is 95%. And then that would mean our alpha is equal to 1 minus 95%. That's our comfort level, of error. Okay. And to create our confidence interval, it's always point plus or minus the margin of error. And the formula is right here. Here's our point estimate, plus or minus z of half an alpha times the standard error. This is the margin of error right here. Okay, so let's estimate this. Point, this is just the difference in the sample averages. So let's get the data. It would be non-car owners minus the car owners. That's the point estimate right there. And the margin of error, that consists of two parts, z of half an alpha and the standard error. Okay, the standard error that we've already calculated. It's up here, right there. And we calculated to do example 9.9. So I'm going to just use that same standard error. And the z of half an alpha, I think we calculated that right here. It's 1.960. But let's just make sure and calculate it again for practice purposes. Okay. Okay, so we have an alpha is 5%. So alpha divided by 2, this is equal to alpha divided by 2 is that 2.5%. And then we have 1 minus alpha divided by 2. Why did I do that? Because I need to find the cutoff, the z of alpha divided by 2. This is equal to norm.s.inv, where you put 97.5% to the left and 2.5% or half an alpha to the right. And here it is. Okay. And again, that's our critical value, right? So the margin of error is equal to the standard error times z of half an alpha. There it is. Okay. So our confidence interval, we have upper, point, and lower. The point estimate is here. The upper is equal to point plus the margin of error. Oh gosh, I hate when that does that. And the lower is equal to point minus the margin of error. And let's decrease the decimals. Okay. So we could see here that the confidence interval goes from negative 0.011 to 0.3 0.31. And what is this confidence interval of? Of the difference in the average GPAs of non-car owners and car owners. Remember, X1 bar is the sample average GPA from non-car owners, and X2 bar is the sample average GPA from car owners. And we see that 95% confidence. We know that difference could be some negative number to the positive number. The null hypothesized value here was 0. Does our confidence interval include 0? It does include 0. That means with 95% confidence, the hypothesized difference, the null hypothesis difference of 0, meaning there's no difference between these GPAs, can occur at 95% confidence. So we fail to reject H naught. Okay? And that's how you use the confidence interval to perform hypothesis testing. It's basically the same thing, but as a critical value approach. But presenting the information slightly differently. Same information. All right, the last thing I want to talk about in this lecture is the difference between statistical significance and significance in magnitude. And that's the last page or so of this lecture notes. Statistical significance versus practical importance or significance in value. There is statistical significance and significance in magnitude. Okay. Something could be statistically significant, but may not be significant in value. Statistical significance is what we have been doing so far. Is there statistics supporting our conclusion? Okay. If we specifically is the statistical analysis, the analysis we are doing, rejecting H naught or failing to reject H naught. That's statistical significance. Okay. Statistical significance generally deals with low p-values. We focus on the difference from the hypothesized value, or does this differentiation exist? For example, in hypothesis testing, we have H naught is p is less than equal to 0.20. Null hypothesis is, the mu is equal to 0. The difference between the two, these are our null hypothesis. What we're trying to do is figure out, okay, does the data show that the null hypothesis can be rejected or fail to be rejected? Okay. So for example, in this first example, is the p less than equal to 0.2 or is it greater than 0.2? In this one, is the mean equal to 0 or is it not equal to 0? Or here is the oops. Is the difference in the two population mean equal to some d naught or not equal to? Okay. Significance and magnitude deals with how different from the 20%, the 0 or d naught. These are different questions. And that's a different question to answer. Okay. For example, Suppose I find a new and improved investment technique. I claim that the technique can always beat the market. I apply my technique and I test my hypothesis, and my returns are higher than the returns when investing in the market portfolio, S&P 500. Okay, so I develop a hypothesis. Mu1 minus mu2 is less than or equal to 0. Mu1 minus mu2 is greater than 0, where mu1 is the average return using my technique, and mu2 is the average return if you invest in the S&P 500. Suppose I can reject the null, and I find proof using data that my technique beats the market statistically. Okay, that is statistically significant, meaning the data shows I always beat the market. Okay. However, suppose my average return is only 0.0001% higher than the market return. Well, yes, I beat the market, and it clearly is shown using statistics. However, is there a difference really in magnitude? No. I only beat the market by this tiny number. Okay? If applying my technique takes, 10 hours a day, while investing in S&P 500 takes nothing, no time. You just put it, set it, and forget it. Is your time really worth this much extra gain in return? Okay? That's the difference between statistical significance and significance in magnitude. Okay? In terms of magnitude, it may not be considered worthwhile or significant, or the significant in magnitude is insignificant. Get them. Okay. However, if suppose we found the difference in this mean, basically my technique is 20% higher than investing in S&P 500, then it's probably worthwhile. There is indeed a difference in magnitude. Okay. Here's another example. Try to beat this into you. Example 2. Men can be found to be taller than women, and that could be true statistically significantly. But suppose the difference is only by 1/1000th of 1 inch. Well, is that really men really taller than women? Yeah, technically they are. But in all intents and purposes, if the true difference is that tiny, 0.00001 inch, then in reality, in magnitude, they're effectively equal height, even though, yes, scientifically, statistically speaking, men are taller than women. Okay. Okay, so that is something we can get into later in more detail when we talk about estimation. We are done with part 2 of the lecture on chapter 9. And we're done with chapter 9. Have a good day.